All right, let's take a look at problem 13. It says if y equaling 5 plus the integral from 2 to 2x of e to the negative t squared dt, then which of the following is true? So for this problem, notice they're saying what dy dx is, and then they want to know what your initial condition is. So this y of 0 means y when x is 0, or y of 1 means y when x is 1. So the first thing I'm going to do is kind of figure out which of these options I like based on what dy dx is. So to that end, I'm going to take d dx of both sides of the expression. So here's d dx of the left side, and then here's d dx of the right side. Okay, so the left side's easy, that's dy dx, so that's nice, that's done. And then on the right side, I'm going to distribute the derivative over addition. So d dx of 5 is 0, which you could write or not. I'll just show that I thought it through. And then I'm going to postpone my thoughts on the right side. So I'm just going to say d dx of the integral from 2 to 2x. And then for e to the, well, I think I'll go ahead and write it in this step, but here's the deal. That is not an integral that we either know how to do at all, or an integral that that we could do in the amount of time that they meant for us to do this problem. So with that said, we're better off actually doing with generalizing the situation, saying, you know, that e to the negative t squared, let's hope it doesn't matter what it is, that it's just some function of t. So in that case, then what would I have? I'd have dy dx is equal to, I'm going to stop writing that 0 plus, but then I'd have, it would be d dx of the integral from 2 to 2x of that f of t dt. And then when I'm done, I'll go ahead and back substitute that function in for lowercase f of t. So now let's use the fundamental theorem of calculus, which would say, hey, if you're doing the antiderivative of f of t, it would be called big F of t, and then you're plugging your upper bound and lower bound and subtracting the results. So we'd have whatever the antiderivative of that function is with 2x plugged in, take away whatever the antiderivative is with 2 plugged in. Okay. Now, just a note, if these statements could talk to you, big F of 2 would say, hi, I'm a constant. So think about that, what that means for its derivative. And then big F of 2x would say, I'm not a constant, but I am a composition of two functions. So think about what that means for its derivative. Okay, so what does that mean? That means that we'll have to use chain rule on this one. So derivative of the outside function would be lowercase f, but then times the derivative of the inside function. And then the derivative of this constant would just be 0. So now I have a rule for dy dx, but it's in terms of f. So if you look up here, f of t is e to the negative t squared. So f of 2x would be e to the negative 2x squared. But then we have this times 2 from the chain rule piece. So you're looking for the option that has 2e to the negative 4x squared as your dy dx option there. Okay, so at this point, just based on the dy dx statement, I would rule a out, b out, c out, so then it's between d and e. So now for choosing d and e, they're going to ask you to choose that based on your initial condition. And one really easy way to figure out which one would be to look at the original problem and just kind of play around with plugging either 1 or 0 in and see, like, would I get 5 out? Which one would give me 5 out? And so let's just play with 0 for a second. This would go from 2 to 0 of this thing. So, and if you think area, this has some continuous function graph, and if you were to go from 2 to any other number not 2, you'd likely have like a non-zero value for this whole integral. So let's just look at one really quick, and this is going to fall into place pretty quick. So put 1 in for x, and notice your upper bound would become 2 times 1 or 2. So the integral from 2 to 2 of any function would be 0. So this whole integral value would be 0 if you're plugging a 1 in for x. And so you'd have 0 plus 5, boom, which is 5, which helps me to rule E in. All right, my friends, I hope this helps. Take care.